In this video, I want to talk about the curve which minimizes the path between 2 points, let's say A and B here. And you have to think of A and B as fixed points. Now, you can think of an object located at point A, where there is some kind of origin. We have a coordinate system here at A. So, for example, this is X and this is Y, pointing downwards. And we have an object which is subjected to gravity, only gravitational forces. And this object is moving along a guide, some kind of path. So you have to think of this as the ground, which has some kind of shape. And this object will stop at B. So we are assuming that it's going to move from A to B. And the question is, what is the path? And in particular, I'm talking about the shape of this path here. So it is some kind of function y which depends on x. What is the function y of x which minimizes the time for the object to travel between A and B? So it will take some time for the object to move from A to B, and we want to find the function y of x such that it minimizes the time, let's say capital T, to go from A to B. One might think that this function y of x could be a line, a straight line going from A to B like this. But this is not the case, and we will show it. Let's start from capital T. So this is what we want to minimize, and we have to be able to write capital T with respect to some variables, and in particular the function y of x. So capital T will be an integral of the small time interval dt from 0 to capital T. This is quite trivial, right? We know that if we define a function s, which describes the path that we are moving on here, so for example, s is the length from A to this point. Therefore, this means that if we take ds and we divide ds by dt, this is going to give me the velocity v of the object, right? Because ds is a small element along this curve. If we divide that by dt, we get the velocity along that curve. So we can rewrite this as integral from 0 to L, the length of the curve, ds divided by v of s. But now we can rewrite the velocity by thinking about the conservation of energy. So the conservation of energy here tells me that the kinetic energy, 1/2 the mass of the object times the velocity squared of the object, is equal to potential energy. But what is potential energy here? It is just mg times y, right? Because at the origin here, we will have 0 equal to 0. So the velocity will be 0. So we assume that the object starts with 0 velocity, and the potential energy here will also be 0 with respect to this coordinate system. And then as we move along this curve, the potential energy will increase if we write it in this fashion, mg times y, right? And also the kinetic energy will increase. In particular, from here we can get v equal to the square root of 2g times y. And from here, we can also rewrite this integral like this, integral of 1 over v of s, which is 1 over square root of 2gy, and then we can rewrite ds like this, because ds can be rewritten considering the two projections of the s. So we have dx here and dy here. So it is the square root of dx squared plus dy squared, and if you factor out dx squared, you can rewrite this as 1 plus y prime squared dx, like this. And then we have to integrate from 0, this point here, along x. So we have to move on the x-axis until this point, which is, let's say, a, and the ordinate here will be lowercase b, for example. So we have to integrate from 0 to a. here. Now, what we have to do is we have to consider this function, this integrand. This integrand is a function of y and y prime. So this will be a Lagrangian. A Lagrangian which depends on y and y prime, and y prime depend on x. So this will be a Lagrangian which depends on y prime, right? And therefore we can use Lagrange equations if you want to find the variation of t and set it equal to 0. By setting this equal to 0, we will find the path which minimizes the time between A and B, the time for the motion between A and B. So dt equal to 0, delta t equal to 0 like this with the variation will translate to Lagrange equations, right? So we have d over dx in this case, dl dy prime minus dl dy equal to 0. So we have to calculate the derivatives of this Lagrangian. Now, the Lagrangian can be defined like this, but in principle, we can also multiply by a constant, and the equations of motion will not change. So this equation here, this equation will not change if you multiply this equation by a constant or the Lagrangian by a constant. In particular, I want to multiply by the square root of 2g so that I can get rid of this factor here in the denominator. So I can define the Lagrangian simply like this: the square root of 1 plus y prime squared divided by y. So if I define the Lagrangian like this and I substitute it into this equation, I will obtain the equation of the function y, so the equation that the function y should satisfy in order to minimize the time between A and B. So we have to calculate a bunch of derivatives, dl over dy, which is equal to minus 1/2 y to the minus 3/2 square root of 1 plus y prime squared. We have to calculate dl over dy prime, which is 1 over square root of y times y prime divided by the square root of 1 plus y prime squared. And then if we calculate the derivative with respect to x of this function, so y prime divided by square root of y 1 plus y prime squared, this will have to be equal to this. So we can rewrite it as minus 1/2 square root of 1 plus y prime squared divided by y cubed. And now basically we can calculate this derivative, but before doing so, let's multiply both sides of this equation by the square root of y times 1 plus y prime squared. This multiplies d over dx, y prime over square root of y 1 plus y prime squared. This is equal to minus 1 over 2 1 plus y prime squared divided by the absolute value of y, but we are going to consider only y greater than 0, and this makes sense. If you think about it, the path that minimizes this time from A to B will be reasonably contained in this region where y is greater than or equal to 0. So we are going on, we will continue like this. Now, why did I multiply by this term? Because it will simplify the calculation of this derivative if you think about it, because this can be rewritten as derivative with respect to x of square root of y times 1 plus y prime squared, y prime divided by the square root of y times 1 plus y prime squared, minus the derivative with respect to x of square root of y times 1 plus y prime squared times y prime over square root of y times 1 plus y prime squared, and this is equal to minus 1/2 1 plus y prime squared divided by y, like this. This first term simplifies here, and the calculation is easier in this form, so we can write y double prime from this term. Then we have to calculate this derivative and multiply it by this, which is quite straightforward, so we get minus y prime squared 1 plus y prime squared plus 2y prime squared y double prime y divided by 2y 1 plus y prime squared, and this is equal to minus 1/2 1 plus y prime squared divided by y. Now we can simplify this a little bit, so we have y double prime minus y prime squared over 2y minus y prime squared y double prime divided by 1 plus y prime squared equal to minus 1/2 1 plus y prime squared over y. This term here on the right will simplify this one. If you put this together with this, you have y double prime divided by 1 plus y prime squared equal to minus 1 over 2y, and you can rewrite this as y double prime times 2y equal to minus 1 minus y prime squared, and this can be rearranged as 1 plus 2y y double prime plus y prime squared equal to 0. Now you can multiply this equation by y prime and you get y prime plus 2y y prime y double prime plus y prime cubed equal to 0. And now this simplifies because this can be written as d over dx of y plus y prime squared. If you calculate the derivative of this with respect to x, you will obtain exactly this function. And this is equal to 0, which means that y plus y prime squared is equal to a constant. And this constant will be greater than 0. From here, you get y prime squared equal to c minus y over y. Basically, you get y prime equal to plus or minus the square root of c minus y over y. And now this can be written like this. You can separate the variables x and y, so you can write integral square root of y over c minus y dy with a plus or minus here. This will be equal to integral over dx. Now we are assuming that the function is on the right part of my plane here, so the positive side of the x values, so we can take the plus sign here. It means that this will be a plus because we are integrating over dx, and this will give me x here plus a constant if you want, but this will be something which is greater than or equal to 0, so we have to consider a plus here. And the integral can be carried out quite easily if we make a substitution. Y equal to c times sine squared t, for example. And if you make this substitution, we have x equal to integral dy will become c times 2 sine t cos t times sine t divided by cosine t dt, and this is quite an easy integral to carry out. You get 2c integral sine squared t dt is equal to 2c integral of 1 minus cosine of 2t divided by 2 dt, and therefore this yields 2c times t over 2 minus sine of 2t divided by 4 plus a constant that I can call d. Now we want x of 0 to be 0 and y of 0 to be 0 because at time t equal to 0 we are assuming that the point starts from the origin, so d will be equal to 0 and x of t will be equal to c times t minus sine of 2t over 2 and y of t equal to c 1/2 minus cosine of 2t over 2. And these two equations describe our function y of x. So this is a parametric description of our curve, and it is a cycloid. It is not a line. I will talk more about the cycloid in a moment, but let me also tell you that this constant c is such that x evaluated at capital T, which is the time that elapses between the starting point and the final point. Starting point is capital A and the ending point is capital B. X of t will be equal to A, whereas y of capital T will be equal to B. So these are constraints that will allow you to find C and capital T if you have A and B. Now, what is this kind of curve, this strange curve, a cycloid? It can be generated by considering a circle. This circle is moving on a plane. It is rolling on this plane. This is the point where there is a contact between the plane and the circle. Let's call it O prime. The circle starts at some point O here. This is the origin. So let's assume that y goes upwards and x goes to the right like this. And this is the center of the circle, which is C. Then we have a generic point P here. Let's draw this horizontal line which intersects the circumference at the point A. This is the radius. CO prime will be the radius capital R. And we are assuming that O prime coincides with O when t is equal to 0. So this length here, O prime, will be equal to a parameter t. When t is equal to 0, O coincides with O prime. And the point P, let's assume that it coincides with also O prime and O. So the angle described by P when the circle is rolling from O to O prime will be this one. Let's call it theta, because at the initial time, let's say when t is equal to 0, P will coincide with O prime and it will coincide also with O. So we can write down the coordinates of the vector OP. We can think of this vector as given by OO prime plus O prime C plus CP. And OO prime is equal to T0. O prime C will be equal to 0R, whereas CP is given by R times the cosine of this angle here, which is 2 pi minus pi over 2 minus theta, and it will be given by the sine of the same angle, 2 pi minus pi over 2 minus theta, like this. And now the cosine of this angle can also be written as the cosine of pi over 2 plus theta, which is equal to minus sine theta. Similarly, this sign here can be written as minus the sine of pi over 2 plus theta, which is equal to minus cosine theta. Now, if you put those together, and together with the fact that t is equal to the angle theta times r, because this length here will coincide with the length that we have on this circle here, this length here, if you think about it, because this circle is rolling on this plane without slipping, which means that as P is moving on this circle, all the other points here on the circle, on the circumference of the circle, will have been in contact with the ground. So if you think about it, this is quite intuitive that if the circumference is not slipping on the ground, then it means that this length will be equal to the length that we have on the x-axis. So t will be equal to theta times r. And therefore it means that the x-coordinate of OP, which we call x, is given by theta r minus r sine theta from the equations that we have above, from the vectors. So from here, if you project this on the x-axis, this is what you get. And similarly, y is equal to r minus r cosine theta. And now, if you set r equal to c over 2 and theta equal to 2 times t, and if you substitute these two expressions there, you get x equal to c t minus 1/2 sine of 2t, and y equal to c times 1/2 minus 1/2 cosine of 2t, which is exactly the curve that we obtained in here, this cycloid, right? So this is one way to think about the cycloid. It is generated by a circumference rolling on a plane like this. So that curve will be the path of the point P, that the point P, let's say, describes on the plane.